I brought my team of folks. So you're going to hear from Dr. Paul Stackhouse, and potentially Falguni will jump in here or there. You'll also hear from Brennan Lean, Brennan Bean, and Carrie Vuyovich. They introduced themselves earlier. There are some projects that were invested in before I started, but highly support and directly relevant to the work that you guys are doing here. So next slide, please. So NASA's Earth Science Division has been investing for years on an observing fleet, decades of observations to observe the changes to our environment. And as you can see here, I'm sure you're familiar with a lot of them, the investments made in the early 2000s, all the way to the planned missions out to 2030. We have worked with the private sector. We've worked with other federal agencies. We have leveraged opportunities to put instruments on the International Space Station. We have come in a bit of a golden age of observations that will help us to monitor the changes in the environment, our climate. We have long-term data records, and we started to look at ways to better serve this information to the public. Next slide, please. So the Earth Science Division is broader than just taking data from satellites. We do a lot of investments in the technology. So we actually do demonstrations with flight, with aircraft. We do the underlying data and compute capabilities. We push those into missions. So the flight actually refers to the various missions that we have there. Research and analysis refers to the RNA research and analysis group that does the Roses calls. So all of the solicitations to the academic sector, federal agency to analyze the data to get great understanding from what we see from the various data sets that we have. Our data and compute section, they're actually taking a lot of this wide variety of information and sharing that openly, free, open science information, most of it cloud-based, and we've been doing improvements there to make our data as readily accessible as we can. And the Earth Action Program is where the Energy Resources Program exists. And that one is now taking the information, taking all the things that have been developed and understanding that have been created through the various other offices in Earth Science Division, and now bringing that to stakeholders. What can the stakeholders use? How can the stakeholders inform the things that we do? So a bidirectional transfer of information. Next slide. Later, or I guess it was March or so, somewhere in March or April of this year, we released a new Earth Science to Action strategy. And it covers the next 10 years, but this is to set the stage for providing the information that are readily available to stakeholders so they can quickly make decisions with it, and be able to have their decisions informed by the best science that we have. Our vision is to have a thriving world driven by these actionable Earth science data. And this really involves working with partners. This is not just a NASA endeavor. We need partners to do this. We need to scale up our efforts to reach as many people as possible, hold hands with our federal agencies, hold hands with professional organizations as you guys that want to actually take information and inform decisions, and build bridges across our enterprise to do this. We want to focus best on the needs of our users, depending on, it doesn't matter where they are, an emergency manager, a farmer, or whatever it is. We want to make sure that we have built enough bridges so we can get to the right stakeholders and inform the decisions they need to make. Next slide. So we have a visual representation of the strategy. I mentioned before NASA's investments in the foundational knowledge. That's the thing you guys know us most for, the nice tech or flights or missions. The ground segments. I forgot to mention ground segments. We have a wide variety of validation ground observations as well. All that foundational information underpins everything that we do. However, on top of that, the next pillar or layer of this is our earth science and applied research, where we build the tools, we build the understanding, we have the community, academic community, help us with this and spread the work around, because we need to partner to understand how it's best to leverage our information, these data sets, and build upon the wide expertise we have in the United States and the world to build these predictive models for our applications that we have and help with the societal benefit areas. On the one right above it, not the next slide, it's this slide. The one above it is the solutions and societal benefit and societal values. So this is where we further tailor, we further do things like what you'll hear from our power program, where we work directly with stakeholders, get their needs, and actually provide them with information that we probably had before, but folks needed it in a format that they could use, an Excel, a text file, whatever it is, because they're on a ship and they need to make a decision right away and they can't get the information. We're figuring out ways to get it to them. The tip of that pyramid, the purple area, we call that public understanding and exchange. And that's now trying to make it easily digestible. So we do have trainings, capacity development activities. We also do a lot of outreach to the public, especially in the new Earth Information System that we created, an Earth Information Center. And I don't know if you're familiar with it, but we just opened a new one at the Smithsonian just recently, where we're actually showing some easily understandable Earth science data to the general public through the museums. And then finally, that arrow there is something else they asked me to lead with the expansion of my duties, which is the virtuous cycle. So taking stakeholder needs and user needs and feeding that back into everything that we do, and vice versa, taking what we've learned from our science and feeding that to our stakeholders. So it's a huge cycle and movement of not just in the bottom of the pyramid, but along the entire way. This arrow actually breaks off into each of those parts of the pyramid, feeds it, and feeds back into it again. So trying to find a standard way to do that. So next slide. So the Earth Science group, as I mentioned, has Earth Action. The Energy Resources Program happens to be one of them, but we have many across the various societal benefit areas: agriculture, resilience to climate and community action, mission engagements, health and air quality. I mentioned the Earth Information Center to you before. Our Satellite Needs Working Group does biannual surveys of all our federal agencies and users to find out what are these things that we should be working on. Let's come up with a solution that could meet many needs. The U.S. Greenhouse Gas Center was the initial thing I was asked to do, and that's trying to help with getting the right information into decision makers so we can mitigate greenhouse gases. So we're trying to empower our communities to find the solution to the challenges that they face every day. Next slide. So the Energy Resources Program, as I mentioned, Allison took it on. She started it, I think, early last year. I'm moving it on. We're trying to improve our nation's capacity to integrate this information, the environmental data from our Earth observations, the analysis and modeling. We're trying to support key decisions in energy production, power systems, management, energy resilience. We're particularly focused on solar, wind, and water, but we realize that the energy weather nexus touches so many things that we may actually need to look a little broader. And we also are looking at what you guys are interested in, which is the resilient, efficient, and sustainable infrastructure, and seeing how best can we serve the communities such as yours. Next slide. So what you're going to hear today is a little bit from Paul about the POWER project, which is Prediction of Worldwide Energy Resources. He's based at NASA Langley. I'm not going to do the offshore winds, but we'll briefly touch on it. Paul will go into some of the other capabilities, and then Brennan and Carrie will talk about our roof and Snowloads project. So I'll turn it over to Paul. Thank you.
Well, thank you, Shanna. And so this is our project we call POWER. We've actually predate the program. We've been working for more than a couple decades now, trying to provide information to users that's really readily usable. And so let me just describe a little bit basic overview of what we do and some of the applications I think might be useful for ASCE, but we do touch on broader applications as well. But first, let me just have you focus a little bit. We have a number of contributors now. We've been able to build up our team, so we are pretty flexible, and we are developing new capabilities and also new partnerships. And so that's why we're really excited to hear and to participate with you. All right, so go to the next slide. So what is POWER about? we really are focused. We have 3 user communities that we've been focusing on, and essentially we're kind of somewhat of a model for that Earth Action philosophy that Shanna just presented, in that we really have started from NASA research. We started because we were asked to provide solar radiance information to help refugees power refrigerators in the deserts of Africa, and that really got us started in providing that information. That we were deriving that information for climate research, but we compute the solar radiance at the surface from satellite measurements and analysis, and we were providing that data and making it available for folks to do that. And then it grew from there. And Shanna mentioned originally we were just providing text files and things, very simple but readily usable. And that's kind of the theme that we've done, even as we've gotten far more complicated through the years, which we'll share a little bit about today. But to the solar radiance, we've also added a complete sets of meteorological parameters, all this from NASA analysis and research, to try to bring these and help people make the decisions they need to make. So the first area was this renewable energy, but it's really just in energy development as a whole. But providing the solar, we provide some of the information on background winds and other information that goes with it, which is very helpful for that community. And to do this, we have developed long-term partnerships, and so we learned how to format the data. We learned what kind of units the researchers, engineers, and consultants used to do projects like solar projects. And then we also started to branch out and talk to those in the building sector that really wanted to monitor energy efficiency and model it for their buildings and understand how their building reacted to the weather. And so we have been working for them. And then, of course, they integrate renewables into the buildings for energy, better energy performance. And so we have supported that. And then one of the last things we definitely do is take time to make sure we provide uncertainty information, and we compare that to surface measurements. Most of those actually are from NOAA, but we also collect surface measurements from other locations and other networks. The last community we've served traditionally is the agricultural community, by providing parameters specifically in formats that they can use for families of crop models. And so that's been a key, and we'll show a little bit about how we've selected formats to provide data in ways that decision support tools use immediately. So I'm going to go a little faster now, but let's go ahead and go to the next slide. So as I mentioned, we're based on satellite analysis and solar irradiance, and we have projects now, a couple missions within NASA. One of them is called Ceres, the Clouds and Earth Radiant Energy System. In fact, the one of our last 2 instruments are flying on NOAA platforms now. But this is to monitor the Earth's radiation balance, focused mainly at the top of the atmosphere, but because they also they process cloud information and aerosol information, and they compute the fluxes at the surface as well. So we have long-term histories of these quantities. We have hourly solar radiance all the way back to 2001. We have dailies back to the early 80s. We provide hourly, daily, monthly, annual, and long-term climatological data products. We also provide thermal infrared radiation. That's really our bailiwick. But let's go to the next slide. It turns out to do a good job with renewables and modeling, you really need a complete set of meteorological parameters as well. So as the solar radiance and the other radiation-related parameters were from satellite analysis, we've used and partnered with NASA's Global Modeling and Assimilation Office, and their MERA-2, using their MERA-2 and their reanalysis data products. So we couple those with the satellite analysis, and they show very good correlation. So we're able to provide long-term data products. In fact, these will be hourly all the way back to the early 80s. And we focus those and provide just the parameters that those communities were focused on really need. So this includes estimates of the winds and precipitation, and of course temperatures, various different temperature quantities, and relative humidity, things like wet bulb temperatures as well. And so those are really needed. And lately we've added satellite analysis for precipitation. It's a separate source for precipitation, but it provides another data product to compare. So next slide. I just included this slide, not to go through it, but really as just something that you can keep and refer back to it. It just lists the number of parameters that we do provide from the solar irradiance, and then a number of what we call value-added parameters, like information on the tilt panels and things like that for solar. But we also provide information about the cloudiness and its periodicity and statistics of when solar is available. And then things like the air temperatures and the wet bulbs and all those that correlate with all that solar radiance. And then in green, I highlighted some of the parameters we feature that I think might be relevant to you, because we've worked, one of our long-term partners is ASHRAE, American Society of Heating, Refrigeration, and Air Conditioning Engineers. Are now incorporated their acronyms, so they're actually just ASHRAE. But I think many of you here are familiar with ASHRAE because they rely on NOAA as well for their surface measurements. And we've been able to come alongside and show that some of these reanalysis products are really helpful for supplementing areas where there aren't surface measurements or there are inconsistent surface measurements. And then we've been able to derive parameters that are very much related to the heating and cooling and air conditioning sorts of design parameters needed. Talk a little bit about that later. Things like heating and cooling degree days for various different thresholds. So we make those available from the daily through the climatological, and those have been very useful. We've also made the winds available in different classes according to wind power classes, and have derived things like the building climate zones. And so I'll show those in a little bit. Next slide. All right, this slide just emphasizes we do work a lot to validate these parameters. So I won't spend too much time on here, but we get independent measurements of radiation and, of course, the meteorology. And this is where we actually do read in NOAA's both the daily summary, global daily summary of the day, and also their hourly. Used to be, I guess, ISH, and now it's going to be transitioned. So we'll be looking forward to working with you there. Next. So we have different services we've set up for those we try to reach. So we have a complete API for all parameters. And that's kind of our backbone. By the way, this is all migrated and works in the cloud. And so we're able to be flexible in the cloud, and we're also able to archive all the data, provide access to the data. If you want all the data, for instance, you can get access to it in Amazon Web Services. We also have geospatial services, ArcGIS types of formats, and different sorts of figures. I'll show you a couple of those in a minute. Then we have a user interactive tool that essentially sends commands to the API, returns commands, but it also does figures and analysis. That's called our data access viewer. And then part of the data access viewer, we're going to look at some future climate information. So that's a special project I'll describe in a moment. And we have new tools coming out where you can actually pull surface measurements and compare the parameters that we're making available. And we hope that this will be flexible and should be released soon. Okay, next. So just a word about the data and access viewer. It just provides access to the data in a number of those formats. And it also provides the ability to visualize some of these parameters, both in time series, but in long-term averages. And we have a number of tools. So if you go to the next slide, so a user can pick their location and pick the community they're in, and then they can pick their time period of interest. They can specify whether they want hourly data or climatological data or daily data. So they have all sorts of options that they can pick. And one of those is to pick your format. So if you work in the building industry and you want to model buildings, a very popular format is the Energy Plus weather data files. And you can order your data right. You can just select an EPW file, and then it gives you all the parameters that are included in those hourly files. So go to the next slide, please.
Paul, just how many more slides do you have? How much more time do you need? I'm just monitoring the time.
So is I. So not too many, but I can skip around too. So
no, we're good. We've got a break built in, but I didn't know whether Brennan was going to speak or Carrie. So I'm just I'm mindful.
I'm looking at about 3 minutes.
You're good.
Okay. Go ahead. Next slide. One of the things I wanted to note is we've actually worked with ASHRAE for a while, and they have what they call their climate design tables for any location in the world. Usually those are only based on surface measurements, but we can provide those data for anywhere if there are no measurements available. And so you can get tables for all these design specifications for buildings. Next slide. One of the things we do is what's called building climate zones. Since we're in a PDF, I couldn't show the little video here, but you can watch. We've done like 4-year rolling zones, 4-year average and rolling zones. You can watch the zones change. So you can actually document with the long-term history, we actually can document what's happening and to different areas. And one tool that we've developed, which is available through our image services, is the ability to take a later decade and subtract an earlier one for the climate zones. And you kind of get this ribbon effect where the climate zones might be changing. These sorts of maps have become standards within ASHRAE. They have a different procedure. They require to get a contractor to do these things. But these sorts of maps are now included in the report they issue every 4 years. Next. So one project we have, and this is, I'll probably just go ahead and we'll describe this and end. But the one project we have is working with our own infrastructure office. And we call it the Climate Adaptation Science Investigation Group. We have a number of work groups. Energy is one of them, but also sea level change and extremes in climate, and a number of other working groups, even wildfires. So a number of our centers have risks related to climate changes, and particularly sea level change for a lot of them. You see many other centers are coastal, but then fire is very prevalent at JPL, for instance. But so there's a number of risks, and we're trying to describe those risks as a group. So next slide. So we've processed and tried to essentially worked with a group within NASA to do their own downscaled data product for each of the CMIP6 models. So we've been working with an ensemble of those models. We've also cut down to 22 of them. But according to scenario here, we're using the scenarios for our analysis. We can do ensemble histories out to 2100. And then we've done things. If you go to the next slide, some of the things were available now, but just at NASA centers, is things like how the heating and cooling degree days change throughout the 2100, and also by month, how your heating and cooling would degree days would change for each month of the year for that later part of the century, and then how your climate zone would change. So those are some of the tools that we have available for NASA centers, and we're hoping to partner to expand this. Next slide. And so this was just looking at NASA centers and their changes. So I'm gonna stop here. If you go to the next slide, so that we're just documenting things. Just want to introduce that we have some things like developing digital twins, and one of those was floods, and with the new NASA. So as NASA gets new measurement systems up, we're trying to work or anticipate working with those data. So if you go to the next slide, this one kind of garbled, but it was animation. But bottom line is they have early adopters. And so one of those things that this technology can do is look at the slopes of water and thus rivers and river flow. So I'm sure that NASA is working with NOAA at some level to look at this, but this I think would be very useful for just current flooding and diagnosing issues related to flooding, but also even applications more toward our interest of hydropower as well. Next slide. So we've actually prototyped a digital twin system to potentially use this.
Paul, I hate to interrupt.
And that's it. That's my last slide. I only have.
Fair enough. All right. Thank you.
Thank you so much, Paul. The point is we have a group that's able to tailor analysis and work directly with users for the formats that they need. So there.
All right.
Now
Excellent.
on to Brennan.
Yeah, so Carrie and I are going to jointly present this. The key point of this title slide is that NASA is bringing together NASA scientists and academics in statistics and civil engineering to try to solve this roof snow load problem. So if we go to the next slide, just to give you a brief overview of that problem, when we're thinking about snow loads in terms of infrastructure design, we're looking at three things. We're looking at the variability of the members that hold up that structure, so the resistance of the structure, the ground snow load, and then the estimated retention of ground snow on a roof. And the reason we do it this way with 2 and 3 is because it's too hard to measure each individual roof directly. So we have lots of measurements of ground snow, less of roofs, and so we try to relate them with this factor. And this project's all about this third point, this retention of snow on a roof. So if we go to the next slide, this piece is really, really important in ASCE 7, which is the codes and standards. In fact, we do a lot with ground snow. NOAA's funding a study on ground snow that I'm a part of, Abby Lyle's a part of. Most of the chapter is about what happens on the roof, and for that we have very limited observations. So what you're seeing on the right here is some of the tables that describe how we relate ground snow to roof snow. At the top, we're talking about thermal factors, so depending on how much heat we expect to lose through the roof, how does that change how much snow we expect to be retained. On the bottom, we're looking at the relationship between slope and retention. So this idea that as roofs get steeper, we tend to retain less snow on the roof due to sliding. So we'll go to the next slide. The trouble that we have, and it was talked about on this slide, but you see it here with this picture, is that most of the data that we have to create all the provisions for Chapter 7 are based on very limited data sets, a few buildings, sometimes even just experimental buildings. Here we see what we've used to determine the coefficient right now in ASCE 7's reliability targeted loads. It's data from northern Canada in the 50s and 60s, 1950s, 1960s. And so the goal is to see if we can use remote sensing products provided by NASA to create new data sets at a much bigger scale than what we have in the history and what we could do with these manual measurements on the roof. Carrie can probably speak to it better, but the reason why this is important is if we can understand how snow is retained, not just at the end of the year, but as a function of the snow season, we can understand how retention might change in a future climate where snow retention characteristics are changing. And so what we're doing right now with NASA, if we go to the next slide, is we've got an academic team, USU, Utah State University, University of Colorado Boulder, and at this stage, we're documenting buildings in places where NASA has remotely sensed observations of snow, from which are at a fine enough resolution that we could delineate between roofs and ground. And we're creating catalogs of buildings, boots on the ground, so that we can figure out, hey, how much of that information about a building can we get either from remotely sensed products or from Google Maps or things like that, but also then to create a set of covariates by which we can relate building geometry and properties to this roof retention of snow. And for that, I'm going to turn it over to Carrie to talk about how NASA's helping this process move along with the next slide.
Yeah, next slide. Great. So then the NASA team, what we're doing is trying to extract some information from different remote sensing data sets to feed to Brennan and his team to do the analysis. So specifically, the information that we're looking at is snow mass information, both on rooftops and on nearby open areas. We're also evaluating the potential to get additional snow information from remote sensing data sets, so roof slope, aspect, material, and thermal properties. And then finally, we're using other data sets to look at calculating the reset frequency. So how often during the winter season does the snow fall off and then build back up on different roofs? We're looking at a number of different data sets. One is airborne LiDAR, spectral reflectance, optical and thermal IR imagery to get snow-covered area, and also stereo imagery for snow depth. And then in situ data or model data as well to turn snow depth information into snow mass. If you go to the next slide. So this is just a little bit more details about how we're using the LiDAR data sets to get the snow mass information. We have a lot of airborne LiDAR data collected during snow campaigns, during the snow season, and then during the snow-free season. So basically, you're just taking a difference between snow off and snow on. It's a high enough resolution that we can extract information from over rooftops. And then we use the in situ and model data to convert that to snow mass. And then we're looking at nearby open areas that seem to be undisturbed to get the ground snow loads. Next slide. I'll turn it back to Brennan.
Yeah, and so the hope is that if we are able to create these new data sets at a scale that would be unprecedented compared to what we have before, we can then inform and update building codes, not just historically, which would still be useful in its own right, but also in a future climate, because we now can actually look at the relationship between the geometry of a structure and the snow accumulation patterns, which we can't do with the small data sets that we have. So that's it for us. I don't know if there's time for questions, but I'll put my email in the chat because I do have to sign off after the break if people have questions after the fact.
Thank you so much, guys.
All right. Is that it, Shanna? Should we open it up for questions?
Yes, that was everything.
All right. Thank you. Megan, can you go back to the...
What would you like me to go back to?
Well, I think we can take the slides down for now.
Oh, of course.
Let's see here. All right. So if do you have any questions for any of the NASA speakers, just either come off mute or raise your hand, whatever makes sense to you.
We do have one in the chat already. Yvette had it. Thank you, Yvette. I hope I said the name right.
Yvette, yeah, just go ahead, Yvette, and ask your question.
Well, on the last one on the snow, and I'm sorry I was a little late for the first one, but on the snow roof, I'm kind of wondering, like setting I understand what they're trying to do, but setting the business case, is there insurance data that documents what it costs or how frequently, or is it more of like that the standards, the life expectancy of the roof is lower, and you can show that also, that building codes would increase that life expectancies?
Yeah. So
how does that build a case, the business case?
So for codes and standards related to snow, what the engineers are trying to do is they're trying to say, what do we need to design for to ensure that the probability of structure failure due to excess loading is below some threshold? And so in order to do that, we have to have some sense of the probability of snow accumulating, but also the probability of snow being retained. And so like the first order goal is to understand the variability, the expected variability in retention, because that would then affect what we design for. So for example, if we find out that more snow is being retained than the code suggests, right now it just has a flat percentage, then we would need to raise loads to account for that increased retention. Conversely, we might find the opposite, and then we wouldn't need to be over designing. So insurance data, while interesting, is kind of tangent to the probability piece of that, but it is still relevant. It's not something we're looking at directly, but certainly I think it could inform like insurance quotes and things like that, insurance projections based on retentions. Are there certain geometries that are more susceptible to excess retention than others? But that would be like a second order goal.
Okay, all right. And I hear that. Thank you for that. I think it could help in that second order for policymakers when you say we need to change the standards, and here's another good reason, because it's costing your
right.
constituency.
I think that's fair across the board with codes and standards in general. We're working to leverage the emerging relationship between the IPG and the risk and reinsurance industry. Bilal and I and Amanda are going to be speaking at an ASCE meeting next week with the finance sector about these issues. I think the ties between building standards, building codes, and reduced losses, and then how that translates to the rate structure, that's an important aspect across the board, because right now, as many people on this call know, only about 30% of jurisdictions have hazard-based building codes now. I know even in Maine, there was a big part of the election was whether or not the building codes in Maine were too strict. So I think that economic angle is something that we need to explore. Joe?
Yeah, one of the things I wonder is areas where you're not going to have a lot of data, that it's very unusual to get a big snow, but when you do get a big snow, that it's far more impactful. So I remember living in Seattle and just seeing some of the boathouses collapse under snow weight, but it's a very rare event. You wouldn't collect a lot of data. So I'm also wondering how you would approach that aspect of not where there's a lot of snow, but where it's a very infrequent event, but when it does happen, it can be very impactful.
Yeah, so that's something that we've looked at with the ground snow, not the roof snow, pretty extensively in other studies. And one of the things that we have to do for that is kind of learn from neighbors. So in Seattle, we see very few but very impactful snows similar to Washington, D.C. And what we find is that the probability distributions that describe those kind of places look very much the same. And so then we're able to understand those patterns, not just in one region, but in all regions that have that same dynamic. As far as it relates to roof snow, again, it's one of those things that these increased data sets would help, and that we could look at places, even places that that have more long-term accumulation, but look at like snow on, snow off at the start of the season versus the end of the season to understand how things are shedding over time, which might help inform, well, if we're in a place that only gets one storm, well, what does retention look like after one storm in other places? And so what we definitely need is we need something more than just a few buildings in northern Canada to describe this. And I think that's what this NASA research provides a promise to fill that gap.
We have at least one person that's not on mute. Bogani? Thank you.
All right, well, thank you. That was a great set of presentations. I guess I'm going to kind of throw out something here. I don't think we have time to explore it, but it's something I want to incorporate into these future discussions. You know, what civil engineering practice is looking for is basically we want to operationalize the process of having this information out there across some ecosystem of federal and private entities and make it more accessible for civil engineers to use in their day-to-day practices. So that doesn't mean, you know, doing kind of a research activity. It really needs to be operational in that they can count on that information going forward. I think the other big part of it is we are looking very much into future projections. Civil engineering practice regularly is looking at service lives or design lives of 30, 50, maybe even 100 years. So the focus on understanding where the projections could fit into that's very much at the heart of our discussions. So I'd like to follow up with that at a future meeting or maybe a second meeting and talk a little bit about how NASA research can fit into an operational flow, maybe through NOAA, et cetera. That, you know, we want the data, but we've got to be able to count on it, and we have to understand how it may change going forward.
Hey, James, let me just make a quick comment on that. I think we've started working with Argonne National Labs on typical meteorological years, and then started talking to Oak Ridge on future typical meteorological years. That might be one. I don't know what statistics that the civil engineering community uses, but that might be a way to, that's the way for the buildings, talking about typical meteorological years. If you can get these projections in a similar statistical format, a lot of these tools can be used if you provide the right uncertainty and bound information.
Well, we're going to be talking a little bit about the most recent workshop report that we did last summer that documents a lot of engineering needs specific to codes and standards. So I think this is a topic that's going to come up multiple times.